Sweet. Good morning, everybody. Glad to see everybody made it back for our second week here. I'm going to give just a few seconds for folks to pile in, get Q camera fired up, and we'll get started. Kitty cat. All right. I'm going to let Nova out. I'll leave his food on the bookshelf here if he gets hungry, okay? Because he's pulling at the door. All right. Okay. All right, so let me go ahead and turn on my screen share here and we can get started. Let's fix that resolution. There we go. Okay. This is section 004, 002. I always forget. I'll get this clear soon. Okay, 002. And today is the what, 11th? Yeah. Okay, so welcome back to Calc 1. Today, we're going to talk a little bit more about limits. Specifically, we're going to learn some laws for limits. This is section 2.3. And then if there's time, we'll make that connection to continuity that we talked about last week. This is section 2.5. And the other topic for this week is going to be limits at infinity. So we're going to see what happens as you, instead of sending x to some particular finite value in the domain of a function, we're going to see what happens as x goes on and on and on, further and further off to the left or off to the right. But I don't think we're going to get to that today. So I won't put that on our little docket here for today. That'll be later in the week. Last time, of course, we introduced these limits and we talked about how to calculate them from the graphs. We talked a little bit about how to calculate them algebraically. So today, when we learn these limit laws, we'll be getting a little bit closer to knowing how to calculate them purely in terms of algebra. But first, we need to know the basic rules that exist around the limit operator. Now remember, everything I put down on the notes here, or everything I put down on the dot cam here is stuff that should go into your notes and should go in nice and clear. If you ever need me to slow down so you can fit everything, don't hesitate to say so. We're going to start off today with a theorem. A theorem in mathematics is just a true statement of great import. It's a true statement to which we refer often. So if the limit as x approaches c, where c is just some number, of f of x and the limit as x approaches c of g of x both exist, then the following things are true. We can take the limit as x approaches c of the sum f of x plus g of x, right? If you know that the limit of f exists and you know that the limit of g exists, then you can take the limit of this new function f of x plus g of x by taking the two limits separately and adding them up. Right, and this makes good sense, right? If I'm asking what y value on the graph of f plus g am I getting closer and closer and closer to as x gets closer and closer and closer to c, you just figure out what f of x gets closer and closer to, figure out what g of x gets closer and closer to, and add those up. That's what f of x plus g of x should get closer and closer to, because each of these guys on their own is doing something we understand. Of course, if this works for addition, it works great for subtraction. There's nothing special about addition here. So if you want to take the limit of f of x minus g of x, that would just be the limit of f of x minus the limit of g of x and there's a bunch of these. If it works for addition and subtraction, it might not be a surprise that it works well for multiplication. If you want to take the limit of the product, f of x times g of x, you can do that by taking the limit of f of x and multiplying it by the limit of g of x. And it works well for quotients as long as the denominator isn't 0. So if we want to take the limit as x goes to c of the ratio, I'll write this in parentheses, f of x over g of x. All right, so you have f of x, you have g of x. You form some new function by dividing them, f of x over g of x, like a rational function or something like that. And then you want to take the limit of that thing. Well, this says you can take the limit of the top and the limit of the bottom separately. Okay, so this basically just says that the limit operator plays nice with all of the algebra operations. The limit of the sum is the sum of the limits. Limit of the difference is the difference of the limits. Limit of the product is the product of the limits. And the limit of the ratio is the ratio of the limits. There are some other limit rules kind of like this, or limit laws like this, that I want to show you. But these ones are the kind of foundational ones. So let me go ahead and show you the rest of these. Oh, here, I need to add something, I'm sorry. On number 5 or number 4 here, we need to add as long as the limit as x approaches c of g of x, the thing downstairs, is not equal to 0. All right, if this denominator is 0, then we're in trouble, then we can't do this. That makes sense, right? Now, if number 5 here, if we want to take the limit of a constant function, then for any c, the limit of a constant function is just that constant. So these first 4 are sort of foundational. They tell us how the limit operator plays with the various algebra operations. These things I'm going to show you now are kind of special cases, or very particular limits that we use often, or some rules that may not be as intuitive or as obvious as the first 4. I think this first one is fairly intuitive. If you picture what the graph of a constant function looks like, it's just a horizontal line. So for any number c, if you try to walk along that graph and sneak up on the x value c, your y values are always going to be the same k, that same constant that the function is outputting. So for any c, the limit as x approaches c of the constant function f of x equals k is just k. I'll hold here just for a second, in case anybody's still writing, then I'm going to turn the page and give you a few more things kind of like this number 5.
Is there a reason you did C, or is it just what you chose?
Yeah, just what I chose. C, just arbitrary symbol here. You could have used A here and use A everywhere throughout.
Okay, thank you.
Of course. All right, so give just a second for people who are still writing, then we're going to come back. Yeah, so we'll do these. Okay. This next guy you can take as being a combination. Sure. If you combine number 5 down here with number 3 up here, you'll get a special case. It says if you want to take the limit of a constant multiple, so you have some constant k times some other function f of x, and you want to take the limit of that, then the constant can pop out. This is the same as k times the limit of f of x. This next one's a little bit tricky. If p is a constant power, and constant is important here. Your book doesn't write this, but I think it's important to make the note. Then the limit as x approaches c of a power of a function like this is the same as the limit of that function all raised to that power. So if you had some function you understood well being raised to a power, and you want to take the limit of that whole apparatus, just take the limit of the function, which is easy because you understand the function well, and then raise that output to that power. All right, we're almost here. Again, if p is any constant power, then the limit as x approaches c of x to the p is equal to c to the p. In other words, you can take limits of power functions just by plugging in. Here, there's only one case we need to worry about. If this is a negative power, like x to the negative first or x to the negative second, something like that, and the place you're trying to take the limit is 0, right? Because that would make this function undefined. You can't raise 0 to a negative power. I think that's about everything you guys need. The book actually goes on with a couple other more verbose things like this. If you look on page 96, which is in section 2.3, you'll see that they explicitly discuss how to handle roots, but it's the same thing as this because roots and powers are the same. And it can be a little bit misleading. I don't want to give you guys too much to chew on. So I think this theorem has gone on long enough. We should get some practice with it. And this is all of the things we need. Oh, the symbol after the word negative here, this is an ampersand. It stands for the word and. So if the power is negative and the place you're trying to take the limit, c, is 0, right, then like an explicit example here would be like limit x goes to 0, x to the negative first. This is not equal to 0 to the negative first, because 0 to the negative first is undefined. Right, that would be 1 over 0. So the little except note here, I've got an explicit example of this in blue. We can't do that. But for any other number c, or any power that is positive, this game works just fine. All right. So let me, I'm actually going to show you an example problem from the textbook here. Do I have this open yet? Yeah, here we go. All right, so here really quick. Here are all the limit laws, the 5 basic ones that we started with. And then they discuss some more explicit things. Let's take a look at this example right here. Where'd you guys go? Let's take a look at this example, example 1 right here. Can I zoom in on that? Oh, I cannot. So maybe I'll copy it down, or we'll just write our own. Okay. All right, so I'm going to graph for us a couple of functions. And let's also do something like this. Okay, so in purple here, I have a function f of x. And then in light blue, I'm going to add a function g of x. And let's do this like, how's about like this? Have him go through here. And then down here, -1. And do we want to do anything weird here? How about not? No, let's not do anything too weird. Let's just do it like this. Okay. So you can see the graphs of the purple function, that is f, and the graph of the blue function, that is g. And I want to calculate a few limits using those graphs and these limit laws. Let's look at the limit as x goes to 1 of about 2 f of x minus 3 g of x. Let's start with this. this is okay. So who can help me out? How would I calculate this limit? What sort of things could I do to get started? Specifically, what limit laws from that theorem can be applied?
First, isn't there multiplication we have to deal with?
Say that one more time.
Isn't there a multiplication we have to deal with because it's 2 times f of x and -3 times g of x?
Yeah, so we do have some multiplication by numbers here. But kind of think about your order of operations. If I wanted to split this up, right, that's my goal, because I have all the information about f from its graph, and I have all the information about g from its graph. So I'd like to split this up so I can use what I know about f and use what I know about g. To do that, we will at some point need to get rid of those numbers, but before then,
Can we find what f of x is at limit 1? And
yeah,
then multiply that by 2?
that's getting closer to the game we're going to look at. So I'm going to be very verbose about this just to make clear exactly what these limit laws say and why they're so useful. I'm first going to split up over this subtraction using the second rule, right? It says that a limit of a difference can be calculated as the difference of the limits. Oops, sorry, I wrote C here. This is a 1. Right, so we have a rule that says a limit of a difference of 2 functions can be calculated as the difference of the limit of the 2 functions. So I first split up over that subtraction. And then, as Adrian was suggesting, I'm going to pop out those constants. So this first piece here will be 2 times the limit as x goes to 1 of f of x. And then this minus is the minus from above. And I'll pop out the 3 also. We'll have 3 times the limit as x goes to 1 of g of x, like this. Everybody comfy so far? So here we use that second rule that said that limits can be split up over subtraction. And here we're using the 6th rule that says constant multiples can pop out. And now from the graph, I can look and see what the limit as x goes to 1 of f of x is. I can figure out this piece now that I've kind of got him alone. And similarly, I can figure out this piece now that I've got him alone. So what is the limit as x goes to 1 of f of x? Well, let's look at our graph. F is the purple guy, right? It's like this. Oh, no. So as x gets closer and closer and closer to 1, what pattern do we notice in the y values, f of x?
It approaches 1.
Mm-hmm. Very good, right? If I'm a little guy, my legs stuck to this graph, walking closer and closer and closer to 1, whether I come in from the right or from the left, my y values are getting closer and closer to positive 1. So this first piece is 2 times 1. What about g of x? What about the blue graph?
0.
Yeah, so this is 2 times 1 minus 3 times 0, which is just 2. Right, 3 times 0 is 0. Everybody comfy with that? Any questions about how we're getting to this answer? Okay.
I actually have a question.
Sure, yeah, Pedro, go ahead.
So it's the limit of f of x at 1, but isn't there a hole where the 1 is? So wouldn't it be 2 or no?
So that's a good question, but this is the whole difference between limits and function values. So I'm glad you asked. Let's come over here just for fun. So off to the side here, we said that the limit as x approaches 1 of f of x. To figure this out, we always imagine there's like a little guy walking along the graph close to but not at 1. And as we get closer and closer to having x value 1, we ask, what do our y values get closer and closer to? I don't care what the actual function value is there. In other words, it's true that f of 1 is equal to 2. But f of 1 is not always the same as the limit as x approaches 1 of f of x. So this is what we were talking about most of last week, is the sort of difference between the function value and the limit. The function value is whatever the y value is on the graph at that x value. And you're right, the function value there is definitely 2. But the limit is all about the patterns. What is the pattern in the behavior of the function as we get closer and closer to 1? As we get closer and closer to 1, these y values really are getting closer and closer to 1. They're not getting closer and closer to 2. That's way up here, disconnected from this piece. So we kind of ask, are these guys going to meet up at any particular y value as they walk closer and closer to each other? And if yes, from both sides, they're getting closer and closer to the same y value, that's what it means to say that that limit exists. And the value of the limit is whatever y value these guys are both getting closer and closer to. So it's a good question. It's a perfect concept to review from last week. But here the limit is 1, even though the function value is 2. Does that help?
Yeah, it does. Thanks.
Sweet. Okay, cool.
And then I'm just confused where you got 0 for 3 times 0.
So
0.
So the 3,
Like where did, yeah.
this 3, and then the 0 is coming from this piece right here. We need to know what is the limit as x approaches 1 of g of x. So kind of just like we did there, I imagine I've got a little fella on the graph of g of x walking closer and closer and closer to having the x value 1. And I ask, are his y values getting closer and closer and closer to something? And we see when we come in from the left or from the right, the y values along the blue graph are getting closer and closer and closer to some particular number as we zoom in on 1. They're getting closer and closer to the y value of this point, which is 0. So the limit as x approaches 1 of g of x is 0.
Thank you.
Feeling comfy? Now, if you guys do want more guided practice with this, right, there is a lot of stuff in the homework, but I recognize that it never hurts to have more practice. One of the things that you'll see me linking to a lot in the modules is Patrick JMT. This guy's actually really good. I don't know him. I have any personal connections guy. I don't make any money with him. I actually used his videos to get through my calculus class like 10, 15 years ago. If you check down here, you'll see he has so many videos. It's crazy. And if we look for limit, laws, or limit, there we go. I saw one, limit from graph. That's the first one that came up. Factoring and canceling, common this, common that. All right, there's all sorts of things on limits here. Showing a limit does not exist, limits by factoring and canceling. So I would recommend, if you want more practice or something, search Patrick JMC limits from graphs. And I bet he's got like, yeah, 5 videos or something that all go into detail on this. And of course, you can rewatch the lectures from last week. We did a bunch of this in lecture last week. Okay. I want to come back here. I'm going to look at this guy. Let me call this x equals 2. And let's play another similar game just for fun. Any other questions on the limit at 1 that we did here, the stuff down here before I move away? I'm going to cover this up in a second. Okay, so if not, here we go. Let's calculate the limit as x approaches 2 from the left of 1/2 f of x plus g of x all cubed. So there's a little bit more of a challenge here. We have this time a one-sided limit. And we also have this power over here that we need to deal with. But if we follow those 8 rules that I laid out just a second ago, everything will go just fine, I promise. So just trust the mathematics and we kind of turn the crank. Thinking about the last example, what's my first step going to look like here?
We break apart the two limits.
Yeah, very good, Adrian. Yep, I've got this big addition in the middle here, so maybe I should start by splitting that up. So I'll say this is equal to the limit as x approaches 2 from the left of 1/2 f of x plus the limit as x approaches 2 from the left of g of x all cubed. Everybody comfy so far? Again, just using that first limit law that says I can take this addition and split it up. I can take the limit of the first piece, limit of the first piece, and the limit of the second piece separately. Now this 1/2 is kind of playing the same role as the 2 and the 3 from the previous calculation. It's a constant multiple, so he can pop out. So I'll have 1/2 times the limit as x approaches 2 from the left of f of x. And now I've kind of got this limit alone. I know how to handle that. In the other guy, I'm going to use rule 7, right? Up here. If p is a constant power, then I can take the limit of the power of that function by taking the power of the limit of that function. Rule 7 is what we're going to use on this next piece. So this will become limit x goes to 2 from the left of g of x all cubed, like this. And our goal in each of these, remember, is to kind of get it down to something like this and something like this that we learned how to calculate last week. So I'm not going to start by drawing any more little dudes on the graph because I don't want to clutter things too much. Can anybody, and preferably somebody I haven't heard from yet today, can anybody tell me what the limit as x approaches 2 from the left of f of x is?
2.
Very good, Mackenzie. Yeah, exactly. It's 2. We kind of look at the graph of f near x equals 2, and we ask, okay, if I'm sneaking up on x equals 2 along the purple graph from the left, what are my y values getting closer and closer to? Well, they're getting closer and closer to 2. All right, as I sneak up on this guy from the left, my y values get closer and closer to 2. So this first piece, I have here 1/2 times 2 plus, and I'll draw my brackets here because we know we're going to have to cube whatever we get from this. What is the limit as x approaches 2 from the left of g of x?
-1.
Excellent. Yeah, thank you, Trump. Oh, and I see in the chat here, everybody else is nailing that too. Yeah, Alma and Luke, thank you guys very much. As we sneak up on on 2 from the left along the blue graph, along the graph of g of x, as I imagine kind of walking down like this, getting closer and closer and closer to 2, my y values are getting closer and closer to -1. So now I have this apparatus, and I just need to clean this up a little bit, and we'll be good to go. 1/2 times 2 is +1 plus, what is -1 cubed?
-1.
Yeah, it's -1 times -1 times -1, which is -1. And 1 plus -1 on a good day, that's 0. Even on a bad day, it's 0. All right. Any questions on this second calculation we did from the graph here? Okay. And I am going to go ahead and turn this page. I'd like to ask just one other little question here. What is the limit as x approaches 2 of f of x?
It
Does
doesn't.
not exist.
Very good. Yeah, this does not exist. This is a DNE. Because the limit from the left, we calculated that just a second ago, the limit from the left as x goes to 2 of f of x, that's equal to 2. But the limit from the right with f of x, that's equal to something else, that's equal to 1. And if the left and right limits don't match, then the overall limit does not exist. So here at 1, the limit of f of x did exist, but wasn't equal to the function value. Here at 2, f of 2 isn't even defined, right? There is no filled in hole anywhere here. So you couldn't even hope to talk about continuity there. But even if one of these was filled in, the function couldn't be continuous there because the left and right limits are different. Okay. Any questions on this little observation? All right, then I want to say a few things here to get us ready to start looking at these things from an algebra perspective. Basically, after this week, almost every time we're going to encounter a limit or a concept revolving around limits, we're going to approach it not graphically, but algebraically. And I want to help you see the connection between the algebra and the graphs. So let me look at a quick example here. You can put a header in your notes. We can say relating limits from graphs to algebra. I know that in your past, you guys have seen graphs with holes in them. And you may have noticed that a lot of these limit problems we're looking at involve graphs with holes in them. Where do holes in graphs come from? Where have you seen those before? What gave rise to a hole in a graph in your pre-calculus classes?
Isn't it when the bottom of a fraction is equal to 0 and then there's a number on top?
We're getting very, very close. Yeah, so it's when there's a factor of the top and the bottom that can cancel. So let me look at the graph of, let's say, consider the function f of x equals x squared minus 1 over x minus 1. This fella, this function, is undefined at x equals 1, right? Because the bottom is 0 there. But we can factor the top and cancel. And here I'm using that ampersand symbol again, right? This just stands for the word and. You'll see me use that a lot. And cancel. So let me show you what that looks like. F of x, which is x squared minus 1 over x minus 1, If I factor the top as a difference of squares, x squared minus 1 is the same as x minus 1 times x plus 1, and I leave the bottom as x minus 1, you'll see that there's a shared factor top to bottom here of x minus 1. That bottom is the same as parentheses x minus 1 times 1. So I am allowed, because there is a common factor top to bottom, and that's the only time you can cancel, I am allowed to cancel these, as long as that factor is not equal to 0. And when we cancel those, what's left upstairs is x plus 1. What's left downstairs is just 1, right? This one is this one. And x plus 1 over 1, that's just x plus 1. Now, this is kosher only as long as x minus 1 is not equal to 0, which is the same as saying x is not equal to 1. So the function f of x squared minus 1 over x minus 1, is the same as the function x plus 1, as long as x is not equal to 1. When x is equal to 1, this bad boy is undefined. It may have been difficult to graph this function from this formula, but I think most people would agree that this is not a terribly hard thing to graph. What does the graph of x plus 1 look like?
A linear graph.
Yeah, it's linear. The slope is 1, the y-intercept is 1. This is something we've been graphing since, 7th grade. Let me see here. I'll do it like this. So x plus 1, mark this as 1. And slope 1, y-intercept 1. He looks like this, right? Now the catch is, at x equals 1, we have a hole, because there was a factor that canceled top to bottom. This should be a straight line. I'm sorry if it doesn't look perfectly straight. Right? Jesus, that's ugly. Right. You get the idea, right? This is y equals x plus 1, but with a hole at x equals 1. This is the graph of f of x. So if I asked you to calculate the limit as x goes to 1 of this function, you couldn't get it just by plugging in. If you plug in, you'll get 0 over 0. If I try, or let's say if I need to calculate the limit as x approaches 1 of f of x, which is the limit as x approaches 1 of x squared minus 1 over x minus 1, by plugging in x equals 1, we get into trouble. Because 1 squared minus 1 over 1 minus 1 would be 0 over 0, which is hard to define. Later in the term, I'm going to talk about things like this as what are called indeterminate forms. 0 over 0 turns out to be an expression you can write down that doesn't actually have any meaning. you can divide 0 by 5, that's 0. You can divide 0 by 10 or 20 or 7 or 0.2. All of those would be 0. But you can't divide anything by 0. Right? The 0 downstairs gives us trouble. So if you wanted to just plug in x equals 1 to calculate this limit, which is maybe tempting to do, you get 0 over 0, which isn't any good. But by factoring and canceling, we're able to get this graph. Is everybody comfy with where this graph came from? Does everybody feel like they could draw this graph themselves if I gave you this function and asked you for that graph following this procedure here? Before I go any further, I just want to make sure we're all comfy with like this portion where the graph comes from. Yeah, of course. So what I notice, Fabrice, is that if I look at this function, the top can be factored. X squared minus 1 can be factored as x minus 1 times x plus 1. That's our difference of squares factoring trick from like polynomials back in pre-calculus. After I factor, I realize that the top and bottom have a factor in common. The bottom is x minus 1, which is the same as parentheses x minus 1 times 1. So this parentheses x minus 1 is a factor that is common to the top and the bottom, so I can cancel it. But you can only cancel factors top to bottom that aren't 0. So this cancellation is only kosher as long as x is not equal to 1. In other words, this function f of x is equal to x plus 1 for all x values not equal to 1. That tells me that the graph of this function is the same as the graph of x plus 1 everywhere except at x equals 1. This might even be worth adding as a note. At x equals 1, this function is undefined because the numerator, or because the denominator is 0 there. But everywhere else, this cancellation is just fine, and f of x is equal to x plus 1. So the graph of f of x is the same as the graph y equals x plus 1, except at x equals 1, where we have a hole coming from this canceled factor. So now let me come back down here. If I try to calculate the limit by plugging in, I get 0 over 0, which is a problem. All right, for us right now, anytime you have a 0 in the denominator, we're in trouble. But if I calculate, if I use the graph of f of x, I can find the limit lim x goes to 1 of f of x equals, well, what is the y value of this hole?
2.
Yeah, it's 2, right? Because it's along the line y equals x plus 1. So this is the same as the limit as x goes to 1. I'll write it all out here. X minus 1 times x plus 1 over x minus 1. Cancel, cancel. Limit x goes to 1. The only thing that's left is x plus 1, which is now I can plug in. Sorry, 1 plus 1 then. 1 plus 1, which is 2. So here's the connection, right? You can see the whole, you can see the y value that is our limit from the graph. And that y value is the same y value you get out of the canceled function when you plug in 1. So I'll give you a second to digest this. How did we know that the y value of that whole was 2? Well, I was thinking about y equals x plus 1, because that's the graph that this thing looks like everywhere except right at that point. Yeah. Okay. So what we're getting at here is that the algebra steps to calculate this limit are the same algebra steps you would need to draw the graph. If you do the algebra that you would need to do to get the graph, that's the same algebra that you would need to do to get the limit. Because of course we know we can get limits from graphs. So exactly the same information you need to get the graph is the information you need to calculate the limit. There's a theorem here. Before I write down that theorem, I want to give you just a second to digest this. Are there any other questions about how we're getting this limit as 2, or the relationship between the algebra, the cancellation, and the graph? All right, bravely moving on. If f of x is equal to some other function g of x at all x values except x equals c, then the limit as x approaches c of f of x is the same as the limit as x approaches c of g of x. Oh, sorry, you couldn't see that top part, could you? There we go. And the important observation here is that statements like this, two functions are equal to each other except at some number, those show up when we cancel factors top to bottom. So for example, x squared minus 1 over x minus 1 is equal to x plus 1 except at x equals 1. So like this is f. And this is g. So by the theorem, above, the limit as x approaches 1 of x squared minus 1 over x minus 1 is the same as the limit as x goes to 1 of x plus 1. And the nice thing is, once you've canceled away that factor of x minus 1 from the bottom, the limit laws with which we began class today are all you need to calculate the limit here. All right, if you want to be very verbose about it, you can say that this is the limit as x approaches 1 of x plus the limit as x approaches 1 of the constant function 1. And now you look at the limit rule 8. If p is any constant power, then the limit as x approaches c of x to the p is just c to the p. Well, that's this guy, right? The power there is just 1. So this first piece I can calculate just by plugging in. I get 1 here. So I'm plugging into this x plus, now the limit of a constant function, which one was that? That was number 5, right? If f of x equals k is a constant function, 1 here is a constant function, then the limit of that constant function is just that constant value. So you get 1 here. And 1 plus 1 is 2. And that's the same thing that we got from the graph. I'll go back through those concepts again really quick one more time. What this theorem says is if you have two functions that are equal to each other everywhere except at x equals c, then in particular, they're equal to each other very nearby c, which means the limit as x approaches c of the one function is the same as the limit as x approaches c of the other function. This is useful because we will often try to calculate limits of functions like this at places where they are undefined. That's why so many of your graphing problems from last week involved holes in the graph, because the places where limits are interesting are places where the functions are undefined. But if you're able to find another function that is equal to that original function everywhere except right at that point, then you can take the limit of this guy instead of taking the limit of this guy. They will be equal. That's what this theorem says. This guy is easy to take the limit of because according to our limit laws, you can calculate this limit just by splitting up and plugging in. The trick is to find this function. So again, imagine I asked you just out of the blue, calculate the limit as x goes to 1 of x squared minus 1 over x minus 1. Our immediate observation is that the denominator is equal to 0 when x is equal to 1, and that's a problem. So what I would like to do is find some other function that does the exact same thing as this function, but doesn't have a problem at x equals 1. The way we found that was by factoring the top and canceling. That other function was just good old-fashioned x plus 1. Since we know that these two are equal everywhere except at x equals 1, I can take the limit of the first guy by taking the limit of the second guy. They will be the same. That's what the theorem guarantees. And then taking the limit of the second guy is easy, you just plug in. Okay. So let's look at one or two little more examples here, something that's not too outrageous. Yeah, that looks fun. I I want to calculate the limit as h goes to 0 in the expression 3 plus h squared minus 9 all over h. If the top and bottom were both non-zero, specifically if the bottom was non-zero at h equals 0, I could just plug in, right? If this were just a polynomial, or if this were a rational function and the bottom wasn't 0 when h is 0, I could just plug in and we would be good to go. So you should always, when you're given a limit problem, see if you can calculate it just by plugging in h equals 0. See if you can calculate it just by plugging in the limit. But here, if I try to plug in the limit, the bottom is clearly 0. The top is also 0, and that's a problem. Specifically, the bottom being 0 is a problem. If I had a graph of this function, I could use that graph to try to figure out the limit. But I don't have a graph of this function. And getting a graph of this function in the form it's in right now would be a little bit tricky. It's not an easy thing to graph. So what I'd like to do is go through those algebra steps that we would need to come up with the graph. But then I'm not even going to bother drawing the graph. I'm just going to go through those algebra steps, and we'll see that when you get to the place where the graph would be easy to draw, you'll also be at a place where the limit is easy to take. In order to graph this function, if that's what I wanted to do, I would square this out, combine all my like terms, and see if I can cancel that h from the bottom. See if this thing is a polynomial rather than a rational function. So what I'm going to do is exactly that. Only I'm going to write my limit along with every step. So limit h to 0. 3 plus h quantity squared is 3 squared, which is 9, plus 2 times 3 times h, which is 6h, plus h squared. And then I still have this minus 9, and everything is still being divided by h. Now what you see is that this plus 9 and this minus 9 are going to eat each other up. So I'll be left with limit h to 0. And please don't forget to write your equal signs. Don't forget to write your limits. This is good notation. As you solve your problems in the homework, please try to mimic the notation I use. It'll save you a lot of stress and it'll save you points on the test. So with these 9s gone, I have 6h plus h squared all over h. Can I cancel the h like this and just get 6 plus h squared?
No.
Yeah, not like that. What do I need to do before I cancel?
Factor out an h.
Good. You can only ever cancel things that are common factors, top to bottom. If you did not factor in your previous step, you cannot cancel in this step. So my next step is to factor. When I factor an h out of the numerator, that's the result. And now I can cancel the common factor h top to bottom. And this is where I am. And to help you see this in the context of that theorem, here's my original function f. Here's my other function g that is equal to f everywhere except at 0. So I'm going to make a little note off to the side here. All right, so here's my original function. Here is my simpler function that is equal to that original function everywhere except at 0, which means in particular that these are equal very, very close to 0. So the limit of this is the same as the limit of this, and that's kind of what we're showing with all of this work. Now that I've canceled the h from the bottom, I can send h to 0 without getting a 0 in the denominator. And I know in that last one, you saw me split this up and give the limit to each of these on their own. But what we're going to do is we're just going to say, OK, well, now I can plug in h equals 0. We don't need to be quite that verbose with all of our work. So if you now plug in h equals 0, you get 6 plus 0, which is 6. And there's no more problems with dividing by 0 because there's no more factor of h downstairs. He's gone. This is a very typical limit problem. There will be a limit problem like this on your first exam, and this is how they need to be solved. I would like it if you guys thoroughly understood why this procedure is what it is. So take a second, look at your notes, make everything match what we have here, and then see if you have any questions. The secret sauce here is kind of coming back to what Pedro mentioned at the start of class, where we had f of 1 being 2, but the limit as x approached 1 of f of x was something else. I don't care what this function does at h equals 0. I care about the pattern as h gets closer and closer to 0. So I don't really care what happens when you plug 0 in here. I care what happens as you plug numbers in that get closer and closer and closer to 0. And the easiest way to figure out what those outputs would be is to find another function that's the same as that original function, this guy, except the other function doesn't have a problem at 0. Okay, bonus round. What does the graph of this function look like?
A linear graph with a hole at 6.
It's definitely a linear graph. The hole, when you say the hole is at 6, well, that hole has an x value and a y value. Which one are you saying?
0, 6.
Yeah, very good. The hole is at the point 0, 6. Fabrice, I just foiled. So 3 plus h quantity squared. Remember, we can't just give the power to each of those separately. We got to follow our order of operations. That's 3 plus h times 3 plus h, which is 3 squared plus 3h plus 3h plus h squared, which is 9 plus 6h plus h squared. Yeah, fair question. All right, so are these things starting to make sense? Can we picture the graph in our head? See the connection between the limits that we were calculating from graphs last week and the algebra steps we're using now?
I understood everything. I just for the very last part where you got 6 plus 0, where'd you get the 0 from?
So what I really did there in the background is I split this up using my limit laws, right? So I can take the limit of the first function, that's the limit as h goes to 0 of 6, plus the limit as h goes to 0 of h. And then remember, for any power function, the limit as x goes to c of x to the p is always just c to the p. So the limit as h goes to 0 of h to the 1 is just 0 to the 1. And the limit of the constant is just the constant. So this piece is 6, and this piece is 0. In other words, I'm plugging in. I'm just plugging in h equals 0. Once I get rid of the h from the denominator, I can calculate this limit just by plugging in. That's
So
what
we're trying.
right? This,
So we're trying to find the number, or we're trying to get the problem to work with the number of like goes to.
right. My goal is to manipulate this thing algebra-wise until the bottom isn't 0 when I plug in whatever this number is. So I blow the numerator apart, cancel, factor, cancel, and now I get down here, this function no longer has a problem at 0. So I can calculate the limit just by plugging in. Let me back up just a quick second and show you a theorem that's not an official part of the class, but is relevant, I think, to the questions you're asking. Here's a question. When can I calculate the limit as x goes to c of f of x just by plugging in x equals c? That is, when x to c of f of x just equal to f of c? Because that's what we're doing to go from here to here. I'm just plugging in the limit, right? I'm just plugging 0 in for my variable. An answer, and it's not a complete answer, but it's a good enough answer for us, if f of x is any polynomial, then lim x to c of f of x is equal to f of c. This is really a consequence of the limit laws. And if f of x is any rational function whose bottom, whose denominator is not 0 at x equals c, then the limit as x approaches c of f of x will also be f of c. So from the algebra perspective, we would like to calculate limits just by plugging in. I would love it if I could always get the limit as x approaches c of f of x just by plugging in c for x. But many functions, we can't do that because it makes the bottom 0, or for other reasons makes the function undefined. But if you're looking at a polynomial, then you can always just plug in to calculate your limit. And right here, what we have is a polynomial, right? 6 plus h is a polynomial in the variable h. It's a linear function. Remember, we asked what's the graph of this look like? Oh, it's a line with slope 1 and y-intercept 6. So this guy, I'm allowed to calculate the limit of him just by plugging in. And so that's what we do. We calculate this limit just by plugging in 0 for h. But I couldn't do that in the original expression, because if we try to just plug in 0 for h here, the function is undefined. So let me show you one or two more examples where we don't have any problems. How about that? Let's do one or two where there isn't any trouble to worry about. Let's see, is this going to be bad news? I don't think so. Yeah, no. Okay, so let's calculate the limit as t goes to 2 and the expression t to the 4 minus 2 over 2t squared minus 3t plus 2. Do we want to do it like that? Let's change this a little bit. 2t squared plus 3t plus 2. I can go back for just a second here. Yeah, sorry. So Fabrice, and anybody else who still needs to write, I will bring this back and zoom out just a little bit in case anybody still needs to write anything. We'll hold here just for about a half a minute.
So for this graph, the line runs through the y-axis at 6.
Yes.
Okay. And then is there a hole at 6 too?
Yeah, so the graph of this function is the same as the graph of 6 plus h, except there's a hole at the point 0, 6. I can sketch the graph here for you
Okay.
if you like.
Thank you.
So really quickly, the graph y equals 3 plus h squared minus 9 over h looks like this. So positive one. I put that 6 in exactly the wrong spot. All right. That's what this graph looks like.
Thank you.
Okay. All right. Yeah, so let's get a little bit of practice with these limit laws explicitly before we have to worry about the case where something is undefined. I'll hold here just for a few more seconds. Anybody still writing? So if I wanted to calculate this limit, let's just try using the limit laws. Whoa, 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 what the fuck? My camera's being a little weird. All right, if I want to calculate this limit, just using my limit laws, I would begin by saying, well, the limit of a big fraction, that should be equal to the limit of the top. So that's going to be the limit as t goes to 2 of t to the 4 minus 2 divided by the limit of the bottom. And now upstairs, this would be limit t to 2 of t to the 4 minus limit t to 2 of 2, all divided by limit t to 2 of 2t squared plus limit t to 2 of 3t plus limit t to 2 of, 2. All right, so if we just go very slowly, splitting everything up, following those limit laws, this is what it starts to look like. And if we want to be exceptionally careful like this is now something we can use our power law on. This would be limit t to 2 of t all to the 4 minus limit t to 2 of 2 divided by 2 times limit t to 2 of t all squared plus 3 times limit t to 2 of t plus limit t to 2 of, did it again, of 2. So if we go very, very carefully through this, what you'll find is that now you've got a limit t to 2 of t, and then eventually that's being raised to the 4. Limit t to 2 of t. Limit t to 2 of t. It's going to be squared. Limit t to 2 of t. So all of these things, oh, I'm sorry, this is a 2. Yeah, sorry. This 2 is this 2. This 2 is this 2. The point is, what you get out is the same thing you would have gotten if you just plugged in 2 for t. So here, as t goes to 2, t itself goes to 2. So this piece is 2. So we have 2 to the 4 minus. This is a constant function, right? Right here, this 2 is a constant. So as t goes to 2, this constant stays 2. And the same sort of stuff happens downstairs. I have 2 times the limit as t approaches 2 of t. So this piece is just 2. So this is going to be 2 times 2 squared, like that, plus 3 times lim t to 2 of t. Well, that's 3 times 2. And then again here I have the constant. That just stays what it is. So compare what we get at the bottom here using all of those limit laws to what we had at the very start. Can we fit it all in here? There it is. Can you guys see all of this? Compare what we have at the end here to what we have at the start here. What do you notice?
Where did you get t equals 2? Or limit t is 2?
So I'm using our limit laws. So the limit laws I used from here to here is that the limit, I'll get down to the question you asked. The question you asked is good. And really there's a few other similar questions I should answer along the way. So I started by splitting the limit top to bottom. All right, this is a t here. So the limit of this fraction is the fraction of the limits. That's this first step. I took this limit and I gave it to the top and the bottom separately. Then in the next step down here, all right, so in blue is the rule I used in each one of these steps. In the next step down here, I use the fact that the limit as t approaches 2 of a sum or difference is the same as the limit of the sum right? The limit of the sum is the sum of the limits. So first I give the limit to the top and bottom separately. And then in here, I had some subtraction, right? So I take the limit of the first piece minus the limit of the second piece. That's how this top becomes this top. And I did the same thing in the bottom. The limit of each of these three pieces that were being added up, I just gave the limit to this piece. That's this. And I gave the limit to this piece. That's this. And I gave the limit to this piece. That's this. Right? So first I split the limit over the fraction. I give the limit to the top and bottom separately. That gets me here. Then I give the limit to each of these little pieces on their own. So the limit of the first piece of the numerator minus the limit of the second piece of the numerator. And downstairs, limit of this first piece, limit of this second piece, limit of this third piece. And now we get to your question. Right down here, I used the power rule here that said that the limit as t goes to 2 of any function raised to a power is equal to the limit as t goes to 2 of t raised to that power. Remember, this was, I think, what, rule 8? And I also popped out the constants. I used the fact that the limit as t goes to 2 of some constant times f of t is equal to the constant times the limit as t goes to 2 of f of t. So we use those two rules here. And then down here, I use the fact that just the limit as t goes to 2 of t itself is 2, right? What does t get closer and closer to as t gets closer and closer to 2? It's almost a tautology, right? It's almost something that doesn't require thinking. As t gets closer and closer to 2, what does this function get closer and closer to? Well, this function is t. So as t gets closer and closer to 2, t gets closer and closer to 2. So here's each step with the corresponding rule.
So essentially you just plugged in 2.
Yeah, that's the point of this exercise. Did everybody hear what Robert just said? That's the big connection. Compare the very top to the very bottom. That's a beautiful observation over. That's exactly what I wanted you guys to see. If you look at this motherfucker up here and plug in 2 for t, you get this shit down here. We didn't need to do any of this garbage. Totally unnecessary. Totally unnecessary symbol juggling.
So quick question, why do we do that? Does it help later on?
No, we don't do this. We don't. So the point here is to show you the consequence of those limit laws. So I want to take a second to digest what was just said, and then I promise, Mackenzie, I will come back and connect to what we were doing before so we can see it. This is a rational function. It's a ratio of 2 polynomials. As long as the bottom isn't 0, you don't need to do all this bullshit. You can just plug in. And as long as the thing down here isn't 0, that's going to be the value of the limit. So let's finish this up. Let me go ahead and write down our answer. 2 to the 4 is 64. No, sorry, 2 to the 4 is 16. 16 minus 2 is 14. So the top is 14. Downstairs here, 2 squared is 4. 4 times 2 is 8. So this piece is 8. This piece is 6. This piece is 2. 2 plus 6 is 8. 8 plus 8 is 16, right? So the limit is 14/16. And here we have all of these delicate limit laws that we've applied very, very carefully. But the result is the same thing we would have gotten if we just plugged in 2 in the very start.
Someone in the chat did ask a good question though. If this is on a test, do you want us to expand this?
Hell no. No, hell no. On a
Okay.
test, I would want you to say this is a rational function and the bottom is not equal to 0 when you plug in t equals 2. So this limit can be calculated just by plugging in. and then give me the answer, 14 over 16, or cancel them, you get 7 over 8. The reason I'm showing you this example isn't because this is something I want you to do all the time. It's to justify the steps we used in the previous argument. So if your function is well behaved at this input, in this case 2, and what I mean by well behaved is the bottom ain't 0, the thing ain't undefined, then you can calculate the limit just by plugging in. And that's precisely what you should do. I want to take a second to make sure everybody is comfy with this, and then I'm going to go back to the example we were just looking at and try to see if we can see that in this context. Any other questions about what we did here or how we arrived at this result? It's all right if you have them, whatever you're thinking. If you're nervous or concerned, I promise you there's at least one other person who would love to hear the questions. So please share if you have them. Oh, shit. All right. Quickly now, coming back, we're asking why can we go from here to here by just plugging in 0? Because this is a function that is defined at 0. It doesn't have any problem. It's the same thing as what we were looking at on that example we were just doing. I would love to be able to calculate this limit just by plugging in h equals 0, but I can't because the bottom is 0. So I have to work with it using algebra until I get to a form where the function isn't undefined at x equals 0 or at h equals 0. Then I can just plug in 0. That's the big game here. Now, unfortunately, I have another class that starts right now, so I have to jump. We've got a little bit over time today. I appreciate you guys hanging out. Take the time to rewatch this video if you need to, and then start on this week's homework. If you need more time on last week's homework, submit an extension request on WebAssign. I'd be more than happy to grant that. If you want help with any of these problems, come by my office hour. I have an office hour this afternoon from 1 to 2 p.m. And that is it. I got a jet. I see you guys later, but please take the time to think about this, rewatch the lecture if necessary.